Today I want to share with you the method to analyze a circuit with diodes. So the first thing that we do is to make hypotheses about the conduction states of the diodes. Then the next step is just to test each hypothesis to see if it is mathematically valid. And when I say that a hypothesis is mathematically valid, we should find that the current in the potential across our diode is positive. For the potential, of course, it depends upon the assumption of the assumption we are making about the diode. For example, if the diode is ideal, then the voltage across it is 0 volt. But if we assume that the diode works according to the first approximation, then the voltage across the diode should be higher than 0.0 volts. Whatever. Let's just take an example of a circuit to see how we can apply this method. So let's assume that I have the following circuit with one diode here, a resistor, and in this point I have minus 10 volts. Here I would have plus 10 volts. This is the diode 1, this is the resistance R1, and this is the resistance R2. So R1 is equal to, I would take 5 kilo ohms, and R2 I would take 10 kilo ohms. And here, from this node, I connect another diode whose the anode is connected to the ground. So this is the diode 1 and this is the diode 2. So there is 4 hypotheses we can make about the conduction states of these 2 diodes. We have 2 diodes, which mean that we would have 4 possible hypotheses. Let me illustrate these hypotheses. So this is diode 1 and diode 2. So if the diode 1, I will then, if a diode is conducting, I would denote it 1, and if it's blocked, I would mark it by 0. So here are the 4 possible hypotheses I have. So here 1 and 0, as I said earlier, this means that the diode 1 is conducting and D2 is blocked. Here the diode 1 is blocked, diodes are blocked, here both diodes are conducting, and here only 2 is conducting. So I have 4 hypotheses. Now, just imagine if I have 3 diodes. If I have three diodes, then I would have 8 hypotheses to test. And if the number of diodes increases, then I would have more hypotheses to test, which is gonna be tedious, right? So one way to avoid doing a lot of calculations when we have a circuit with a lot of diodes is to try to analyze the circuit visually without doing any calculation. And I will show you how we can do this. Okay, so let me first erase this. So let's analyze visually this circuit, and we will try to figure out which diode is conducting without doing any calculation, just by following logic. So before starting to analyze this circuit, it is worth to mention that the diodes here in this circuit are equivalent to a potential difference of 0.7 volts when they are conducting. This is, of course, the first approximation of the diodes. Okay. The first thing I can see here is that the highest potential is in this point, 10 volts. In other words, the current has to flow from this point to the rest of this circuit, because this is the highest potential in my circuit. In other words, I can say that the diode 1 is conducting. So, since diode 1 is conducting, only two possibilities are left, because remember, there is 4 possibilities: 0, 1, 0, 1, 0, 0, 1, 1. So now, since the diode 1 is conducting, then I have only 2 hypotheses left, which is this one and this one. So the diode 2 can be either conducting or blocked. So now, since I'm sure that the diode 1 is conducting, how can I know that how can I know the state of the diode? Is it conducting or not? So what I can see here in this circuit is that I have a voltage divider. So this is the voltage divider. What I will do here is to imagine that this diode here does not exist. So I will just imagine that this here does not exist. So in this case, I can say that the potential in this point is positive. And the reason is because this resistance R2 is higher than this resistance R1. Okay, let me explain. When we have a voltage divider that is made of 2 resistors that are equal, for example, in this case, R and R, so these 2 resistances are equal, then the potential drop here is equal to the potential drop here, right? But let's assume in this case that R2 is higher than R1. If R2 is higher than R1, then the potential drop across R2 is higher than the potential drop, or the potential drop across R1, right? This is obvious. This is obvious because the current here is the same and R2 is higher than R1. So we can use this information to analyze this circuit. So let's come back to our circuit. So here, the entire voltage drop from this point is 20 volts. But since R2 is higher than R1, then the potential drop here across the resistor R2 should be higher than 10 volts, right? So VR2 is higher than 10 volts. In other words, the potential in this point, let me call it B, should be higher than 0. The potential in the point B should be higher than 0. So let me just illustrate more in detail this point. So VR2 is equal to VB minus 10 volts, which is plus 10 volts. So we know that VR2 is higher than 10 volts. And from this we can conclude that VB is higher than 0 volt. So I hope that this point is clear now. So now, if the diode, if we connect here a diode, the same diode D2, what would be the potential across it? VD2. The potential across VD2 is equal to 0 volts, the potential here is 0 volts, minus VB, right? And since VB is higher than 0, minus VB is smaller than 0. So since the voltage across this diode is smaller than 0, is negative, then this diode is going to be reversed biased. In other words, this diode is going to be blocked. So now, our conclusion from this analysis is that D1 conducts and D2 is blocked. However, it is a good idea to try to see if the math will work out, if this assumption is valid. So, in order to do that, I will just do the calculation of the current through this diode. But first, let me draw the equivalent circuit that is equivalent to this condition. So here we'll have a diode. The equivalent circuit to the diode 1 is just a potential that is equal to 0.7 volts. Here I have the point B. Here I have another resistance, and here minus 10 volts. And this circuit here is disconnected because the diode is blocked. So there is no need to draw it again. I will consider that I will label the current that passes from here ID1. So now what I want to do is to calculate this current ID1. So the Kirchhoff's voltage law will give me 10 volts minus 5 kilo ohms ID1 minus 10 kilo ohms ID2 plus 10 volts. This is equal to 0. So this would give me ID1 equal to 1.28 milliamps. So ID1 is positive, which means that the diode 1 is conducting, so this assumption is correct. If, for example, ID1 is negative, then this assumption of diode 1 is conducting would be simply wrong. So from this current, I can conclude the voltage in the point B. So VB is equal to 10 volts minus 5 kilo ohms multiplied by ID1, which is 1.28 milliamps. So this gives me VB equal to 2.9 volts, which is higher than 0. And if I want to calculate now the voltage across the diode 2, this diode here, so this is VD2, this is the ground, so VD2 is equal to 0 minus 2.9 volts which is a negative value. This is the reason why the diode 2 does not conduct, because simply it's reversed biased.